Da da da. Newton's law of cooling. Okay, so this is number 11 from the thermodynamics set. Although it says 1 here, it's really an 11. What we have here is this equation here for heat transfer due to conduction, so two objects like touching, where T2 is the temperature of the heated or cool side, and the environment is the other side, right? They're just really whatever. They're two sides, and what we need to recognize here is that as the temperature of one of your objects is either being heated up or cooled down, the temperature difference is becoming closer and closer and closer. And what's actually going to happen over time is it's going to kind of like bottom out. So if we have a graph that looks a little better than that, if we had a graph that looks like this, what's going to happen is at some point in time, the temperature is going to come down and the temperature is going to come up, and they're going to reach some equilibrium, and they're going to go in this curved fashion here, because that heat transfer is constantly changing. And anytime we have something that is constantly changing, or it's changing due to the rate that something else is going, we need to start thinking immediately about things like natural logs. Whenever we saw this for charging capacitors and whatnot, natural logs popped up there, so we might have an idea that something like that is going to come up in this case here. We're just going to try to set up this derivation, and this is what is known as Newton's law of heating or cooling, to go through that. So what we're starting with here is this equation, and let's rewrite this a little bit. So some of you might not be in calculus, some of you might be, but let's rewrite this Q up here. Let's write that as MC delta T. And whenever we actually say a delta T here, or a change in temperature, it is nice to think of that as some very small change that's occurring, because this Q here, this Q is the small amount of heat transfer in some amount of time. So it's going to be MC and then a delta T, so some small temperature shift, which we could write as dt in the world of calculus. And if we wanted this for some amount of time, well, if we want it for a very small amount of time, we could write this as dt. Note these are two different t's here. Top is temperature, bottom is time. And then this is going to be equal to K, the thermal conductivity, A, cross-sectional area, T2 minus T environmental, all divided by some cross-sectional length there, or so some length of the material itself, okay? So when we're looking at this, this is kind of our setup here, and now it's just a matter of solving things out. We need to bounce items around so that the temperatures stay together and then everything else goes to the other side. In doing this, what we'll find is we're going to get dt divided by our temperatures, so that's going to be T2 minus T environmental, and that's going to equal Ka over MCl, because I brought the MC underneath. And then I'm bringing this dt up top, so we're going to get a dt over here. Now, when we look at this, because we've got the dt for d temperature and the dt for d time, I know I'm going to have to integrate this over some long period of time, and over some periods of temperatures. So when I do this for time, we're going to start at time 0, and we're going to end at some time later, t, for my integral, for the bounds of it. On the left side here, we are going to have some idea in terms of a change of temperature and amount of time, and we're going to bound this from some initial temperature to some final temperature here. And in our case, T2 is where we're beginning the temperature, and the environmental temperature is where we're going to end up over a very long period of time, right? Now, one thing to note here, what we're going to do in this problem is we're going to set this up as a Newton's law of cooling, and that means that this MC delta T up here, this is actually energy lost, so there's a negative here. So I'm just going to actually pull this negative over to the right-hand side and deal with it over there. When I do this, we should see this quickly. On the left here, we're going to get a natural log in a second. We're going to have to do a little bit of upper minus lower and deal with that. But on the right, what I quickly see is I'm just going to have minus Ka over MCLT. And on the left here, I get this natural log. I need to be a little bit careful here when doing this natural log. I'm going to get the natural log of this quantity, T2 minus TE. So we do this on the left here. I probably don't actually want to make this the environmental. In theory, it'll hit that, but we'll just call this some temperature later. So when we do this, we're going to get the natural log of, and plugging in the upper and lowers for T2, because this is, TE is just some constant here. It's just some number. I'm going to get T minus TE minus the natural log of T2 minus TE. And then using log rules here, we can see that this is actually the natural log of T minus TE over T2 minus TE. And that's going to equal all of this. And then because nobody likes logs in their life, we exponentiate both sides. So this goes away, and we get e to the negative Ka over MCL T. So this looks very similar to what we had earlier on in the year. And at this point, it's just a matter of moving some objects around. I can take this quantity, multiply it over in front. So I now have T minus T environmental equals the difference in temperatures where it began, T2 minus TE. So this is like the initial starting point, times e to the minus KAT over MCL. And then I'm just going to add this environmental temperature in at the end. And this will give me temperature as a function of time. And what's really cool about this is that whenever time equals infinity here, whenever this time equals infinity, this entire term goes away because it's effectively going to be 0 at that point. And what we see is that T, the temperature of our object at an infinite amount of time, is just going to be the same temperature as the environment. They're going to reach in equilibrium. But we do see that we have some starting point, and then we ramp down, or if this was positive, we could ramp up to that. So that's how we can do Newton's law of cooling. A little bit of a pain in the butt in terms of setting it up and then running the algebra, but it's something that is similar to what we've seen in the past. The real issue here tends to be these bounds, and even I made this mistake up here calling this TE. What am I doing? But these bounds just form a pretty tight log rule, and then that's a little bit changed from when we did the discharge and charging of a capacitor. Okay? But with that, that problem's finished. Newton's law of heating or cooling, specifically cooling in this case. Till next time, adios and take it easy.